Okay, so we're back this week and we're going to be talking about the distribution of the sample mean. So the sample mean should be a quantity you're familiar with. I certainly expect that you studied this before you got to the course. But basically, the sample mean is that formula we've always used where you add everything up, sigma xi, that means the sum of x's. So let me highlight this. So sigma xi, you add everything up and then you divide by n, which is the same thing as multiplying by 1 over n, right? So this should be something that we're all familiar with, the sample mean. And remember what we're doing is we're using sample means to estimate the population mean. And really what you want to know in science is you want to know these population parameters. So these population parameters, these are values that exist in God's data set, right? So if I'm looking at, say, the average SAT score among those in Los Angeles, I would have to get, if I'm narrowing it down even more to like a 16, 17, 18-year-old population, I can do that. But I have to get every single person in the population in a data set to actually get that mean. Now that's unrealistic. So we're going to take samples of that population in LA and we're going to estimate it. And our sample statistic X bar will be our estimate of mu. Now, there's also other types of population parameters. There's the variance, which we estimate with the sample variance. There's also sample proportions, which we'll learn about in the second half of the class, which we estimate, population proportions, which we estimate with a sample proportion. So again, returning back to this idea of sample of statistical inference, that's what we're trying to do. We take a sample and we estimate some parameter. Now there's two ways that we can estimate data. We can use point estimation, which is what we've been doing to this point. We basically take our sample mean and that's a point estimate. Why? Because it's a single point, a single number you get from your sample, right? But we could also move to interval estimation, and that's going to be the focus of this week. And an interval estimation, instead of giving me like X bar is 78, as we'll see later, I can create a 95% confidence interval. And that could be between 80 and say 85. And actually, hold on, let me redo that. If I have a sample mean of 78, then what actually has to happen is that the point estimate of X bar is right in the middle of the confidence interval. So usually you can see here the form is X bar plus and minus how much error you make. And because you're plus and minusing, the X bar, the point estimate is right in the middle of the confidence interval. So it's a symmetrical interval, the midpoint of which is your point estimate. And here we're talking about the sample mean. That's what we're focused on this week. So you can create a confidence interval for any statistic, including sigma squared, p for proportion. But this week we're focusing on the sample mean. So looking at the sample mean, it may seem kind of strange when you first start thinking about it, but the sample mean actually has a distribution. Remember, the word distribution tells us how a certain variable or statistic behaves. If it has a distribution, it means that when I do study number 1, study number 2, study number 3, I'm getting a range of estimates of the sample mean. They're all valid estimates. And they're estimating, again, mu. And actually, hold on, there's a little typo here. This actually should say S squared, and that should say S sub X, because these are supposed to be statistics, not population parameters. So I'll correct this and upload a new one. But every statistic has a sampling distribution. And the reason why it has a sampling distribution is because when you sample, you use a random sampling technique. You don't have everyone in the population. So because you randomly sampled and other researchers randomly sampled, you're each going to get different estimates of the population mean. And those different estimates form our sampling distribution. So let's say we have something like X, we can let it be test scores. Let's say that this right here is the distribution of X. Oh, let me scroll down a little. Well, if I want to give a estimate of the sample mean of X, then first we call that X bar. The bars denoting we're talking about the mean. But notice how, let's say the sample mean is mu, let's say the average test score is 70. Well, the sample mean is going to be centered over 70 as well. So the first thing to note is the sample mean has the same mean as the overall original distribution X. So remember what this is, imagine you have test scores up here in the first quadrant. Then when we move down here, imagine now I've taken a mean estimate. So say I have n equals 100. I have a random sample. I have X bar 1 from that first sample. But I can keep going, right? I can do a second sample of 100. And then I can have X bar 2. And these X bars, they're all going to be kind of down here, right? And because we're using a good formula to estimate the mean, they're going to be huddled right around the true parameter mu. And notice how, like any normal distribution, most of the density, most of the sample means I get are going to be close in the middle to mu. But you can get some strange outlying results, right? If you just get a really biased sample just by bad luck or maybe bad sampling design, that's completely possible. So notice that they share the same mu, but notice how the distribution for the sample mean, which is the second panel, is a lot skinnier, right? There's a lot less variability. You can see that visually, right? Everything is closer to mu in the second picture as compared to the first. Now we can see it visually. We can also see it in the formula, right? So those sigma squared is the variance of X. But when we look at X bar, notice sigma squared is still there, but now we're dividing by n. And so what that dividing by n tells us is that as we get more, as n goes up, we get more and more people in our sample, the variance of this distribution is going to be shrinking. So if I say the blue line is n equals 100, then I could say the red line is n equals 200. And you notice how I'm going to get better estimates of the mean, right? Everything is closer to mu on average. So adapting to this idea that X bar or every statistic has its own sampling distribution. It's a theoretical concept. It's abstract. When I first came across it, I thought it was pretty confusing. So if you feel it's a little confusing, I'd say join the club. That's a pretty consistent response to seeing this idea, because usually how we're trained to think is we get our sample and then we compute X bar and that's it. It's just one value. But the thing we have to remember is that we've gotten X bar to estimate the thing we really care about, the population mean. If I go back and do 10 studies, I get 10 different X bars, even if mu is unchanged. Okay, so in this picture, we show the sampling distribution of X bar. Notice it's normal. We like normal distributions because we're really comfortable with that shape. So a natural question is, well, when is the distribution of X bar going to be normally distributed? Well, there's two things this depends on. First of all, if the underlying variable we're describing X, if that thing is normally distributed, we know beyond a doubt X bar is normally distributed. There are proofs of this. We're not going to go into the mathematical proofs. I'll say, take my word for it. There's some stuff in the book about it. There's a lot of stuff online, but you don't really need to dive into verifying why this is true. The same is true in the second one. Just take our word for it. It's beyond the scope of class. If you want to get into the mathematics there, then let me know. But really, you can just take these two as true. You don't need to worry about proofs or anything like that. In the second case, if X is not normally distributed, then it turns out X bar might still be normally distributed according to the central limit theorem. The central limit theorem is probably the most important theorem in all of statistics. And it says that when the sample size is large, X bar will be approximately normally distributed, even when X is not. Okay, large. What does large mean? Well, that's a bit ambiguous in the definition. You're going to come across this in different books and literature, and different books will use different thresholds for how how big enough is large, but most commonly I've seen 30 where people start saying it's large enough. So we'll talk more about that 30 rule, but to look at where the 30 rule comes from. So let's look at figure 7.6. Here I have a normally distributed x in the top row. Here, this is called an exponential distribution, right? Definitely not normal. And then the third one, we have an x which is called the uniform distribution. Now, if I take two random samples from this x, look, I can estimate the sampling distribution of x bar. Notice it's normal when it's normal, but notice the variance is smaller. And as I go up to 10, as I go up to 30, notice how the variance is shrinking the sample mean, right? I'm getting closer and closer to the true population parameter mu. And mu, you know, that's what this dotted line is. Every distribution here is centered over mu. Now look, when the distribution is not normal, so we're looking here in the second pane, that's an exponential distribution. Notice how if I only take two, the distribution of x bar is kind of wonky. Definitely not normal. It has some positive skew, as indicated by that rightward tail. When we get to 10, okay, looking a lot better. Almost normal, not perfectly normal. By the time we get to 30, I mean, it's so close to normal, we're basically saying it's normal. If it's uniform, notice again, starts out definitely not normal because there's like normal is curvy, right? Bell shape. It's triangular, not what we're looking for. By the time we get to 10, looking a lot better. By the time we've gotten to 30, no matter what the distribution of x is like, we're basically good. So it's possible you have like an insanely crazy distribution, like bimodal or something like that, or massive skew. In that case, it would take more than 30 to get to a normal distribution, but those are very rare, far and few between. So in this class, we're going to go with the rule that when you're at 30, we can assume a normal distribution of the sampling distribution. Sorry, of the sample mean distribution. So x bar is normally distributed under two circumstances. First, x bar is normally distributed. We need no assumptions there. Secondly, x bar could be normally distributed even if x is not, according to the central limit theorem. Here, we need to have a large sample, and we're assuming that that large sample is 30. So once you're over 30, we're saying x bar is normally distributed. Case closed in this class. And for most of your practice, that will be fine too. So again, some people take different numbers. So looking at figure 7.6, there's two important concepts it shows. First of all, the one we've just been talking about, that when n is 30, the distribution of x bar is approximately normal no matter what the distribution of x is. Okay, that's great. We need to understand that this picture is basically how we're justifying in the course that when you get to 30, we have a normally distributed sample mean distribution. Second, the standard deviation of x bar will always be smaller than the standard deviation of x. So look here, x has some spread. Notice when we go to x bar, there's a lot less spread because here you're just sampling test scores from the population. Here you're sampling mean estimates when you've taken 2 people from the population, when you've taken 10 people from the population, when you've taken 30. Notice how the sample mean, as you sample more, just shrinks and shrinks and shrinks. And so this gives us the quantity sigma sub x bar. We call that the standard error of the mean. And literally what the standard error of the mean is it's the standard deviation. That's what we say down here. The standard error is the standard deviation of the sample mean distribution. So standard error is a very special type of standard deviation. So, and how I like to draw standard deviation in these things is kind of think like, you know, this is how much variability is kind of. So notice that as n is 2, we start out with some standard deviation or standard error. But as n goes to 10, the standard error is getting smaller. By the time you get to 30, in this example, the standard error is tiny, right? You're getting really close to the true population parameter mu. So if you were to describe the standard error of the mean in one word, it would be precision or accuracy. It tells us how precise our estimate of mu is. Notice here, the standard deviation or the standard error is really small, meaning we're very precise. Here, we only have 2 people we're basing our sample mean on, so we can be all over the map there. So there's more error, a larger standard error in this picture. There's a smaller standard error here. Okay. So we can work with the distribution of X bar now that we've studied a few of its fundamental facts to answer a couple questions. So what if you're asked to describe the sampling distribution of X bar? So these kinds of problems, they're going to typically all be the same. They're going to give you some mean. They're going to give you some standard deviation. I like to always write the distribution of X is 125, that's our mean, and the variance is 21 squared. So the standard deviation is 21, so the variance is 21 squared. Remember how we like to write these things? Usually it's mu sigma squared, which is why I put the squared there. Okay, so that's the information I'm starting out with, and I know further that the sample size is 49. Well, I can go ahead and tell us some stuff about the distribution of X bar. First of all, the mean is the same as an X. So the variance is going to be 21 squared over the square root of 49. Right, and so that's going to be 21 squared over 7, to be more precise. Now, I don't really like working with variance. I'm sure you're becoming the same way. Notice I have put the variance here. I prefer the standard deviation. So the standard deviation is 7 over 21. Sorry, 21 over 7, which is 3. So the standard deviation of X bar is the standard error of X bar, right? Standard error is the standard deviation. It's a very special type of standard deviation, which is why we've given it its own name here, the standard error. So we've drawn down here the original distribution of X and the distribution of X bar. We can draw it, we can visualize it, we can see it, etc. Now, last week we learned z-scores and the z transformation. And we saw that you can z transform anything. That's a numeric variable. If the underlying distribution of that thing you're transforming is normal, then you can even go a step further and start talking about probabilities. Remember how we went, let's go this way first. We went from X to Z to probability statements. We're going to do the same thing this week, except this week we're dealing with X bar to Z to probability statements. So in this problem, we're given the distribution of X bar, normal, remember? When n is larger than 30, we can assume it's normal. When the distribution of X itself is normal, we know X bar is normal distribution. So here we have the population mean, 125. And the standard deviation of the distribution of X bar is the standard error, which we calculated to be 3. So 3 squared, because remember, the standard error is the standard deviation. We usually put the variance in that second spot, which is why I put a little squared. So those are the facts we're starting out with. So how do we convert X bar to Z? Well, it's the same transformation, X bar minus the mean over the standard deviation of X bar, which we've seen this week. It has a very special name, the standard error of X bar. And so this math takes place right here. We're just plugging in the values. So in this problem, we got a value from our sample of 123.2. but we know the population means 125, so we plug that in for here. And then 3, as we calculated above, is the standard deviation of X bar. So the standard deviation, or the standard error, goes in the denominator. We plug that all in, we get negative 0.6. Notice if the mean is 125 and our X bar is 123, we're below the mean. So we can do a little gut check. We should have a negative value, and it should probably be pretty close, like not too big, because we're not too far from 125. So what this means is we are 0.6 standard error units below the mean. So that means if this is the distribution of X bar, our 123 is here, right? So if you convert that to Z units, that's negative 0.6, and then the 125 would be at 0, right? If we convert the X bar distribution to a Z scale. So in this class, anytime you see large sample, what does a large sample mean? We're talking about N is 30. When it's N is 30, we're going to say, okay, we're in that large sample case. Now, why do we care about this large sample thing? That should be N. I will correct that. So when N is large, it doesn't matter what the distribution of X is, because the central limit theorem tells us that X bar will be approximately normal, even if X is not normally distributed. So that's why we care about this when N is large situation. So we'll always be able to assume X bar is normally distributed with mean mu and standard deviation sigma sub X bar equals the standard deviation of X divided by square root of N. We call this again the standard error of the mean. But here's the thing. This sigma, written in Greek, is a population parameter. Remember, the goal of statistics is we're estimating these population parameters because they're unknown. Okay, so, you know, if you have like a sample of 2 million, you know, you can take your estimate of S and say it's basically so close to sigma, you know, and if you had like such a big sample, it would look like this. We can basically say it's true, right? But what if we don't know sigma? What if we have just like 10 people from the population? We don't really have a good estimate of it. So we're going to run into issues there. Next week, we're covering what to do when sigma is unknown. So this week, we're going to say, by the law of large numbers, that when the sample size is very large, S is going to be close enough, and we can just assume that S is known, that the sigma is known. And that's just because we have such a large sample, our estimate's not going to be too different from the true population parameter. So there's two ways that we're going to be able to construct confidence intervals. And what you're going to have to do in test and homework situations is you're going to have to basically choose between case 1 and case 2. So when case 1 is known, that's what we're doing this week. We use a Z distribution. Next week, we're going to cover case 2 when sigma is unknown. So the sigma known versus sigma unknown, we'll talk more about it next week. But what we're talking about, if you have the distribution of X, it's a normal distribution, it's got some mean, and it's got some variance, right? You don't actually know the parameters. So this is what we mean by sigma is unknown. You know, you're dealing with a new population. There's not a huge literature on it. We don't know what the typical range of variability would be. So, you know, when we construct a confidence interval for X bar, we have to think about what we need to do. So the confidence interval for X bar looks like this. So this is a two-tailed confidence interval test. So confidence intervals for the mean. So the first case, which we're looking at this week, if N is larger than 30 or sigma is known, we're basically using a Z distribution. So when I say use a Z distribution, the thing that's going to change in case 1 versus case 2 is this part. So notice this week I've put a Z distribution. That's a critical value of, and maybe I should even put a star here. It's usually what we like to do for a critical. That's a critical value in the Z distribution. Remember, a critical value is some value of Z that cuts off some percentage in the tails. So we'll look at what we mean by Z alpha over 2 in a second. What we first need to realize is that this thing we were writing earlier, we were writing the standard error of the mean in this way, right? That is a parameter. So what do we do with parameters? We take sample estimates because we don't know what they are. We don't have everybody in the world and the population is sitting in a data set. We estimate them with sample statistics. And so that's what this is saying down here. And that is a ingredient of the confidence interval. So notice the notes they actually wrote. There's the population. You can create a confidence interval for the population, that's in blue. But what we really have to do in practice is do what we see there in red, because we're dealing with sample statistics. So what we really need to do then is we first need to recognize that, hey, we don't always know the standard error of the mean, but we can always get an estimate of it, right? The sample statistic, it's just the population standard deviation of X divided by the square root of N, as we see down here. So in the confidence interval, there's 3 things we have to note to calculate it. The first is, number 1, the sample mean. We know how to do that. The second is we need to estimate the standard error of the mean. Well, we learned how to do that above. The formula is right here. We'll be getting a lot of practice on that. And the third thing we need to do is figure out what the critical value of the relevant statistic is. So the Z alpha over 2 is what we need to dive into next to construct this confidence interval. So what is this Z alpha over 2? So let's talk about alpha first. Let me clear all this. Alpha is your level of significance. And I'm trying to. And it's also the type 1 error rate. So let's assume that what we're going to do is we're going to be getting into hypothesis testing in the next few weeks. So we're going to learn how to test a null hypothesis, say mu is 0, versus an alternative that says mu is not 0. So basically, let's assume this is a Z distribution. We know it's always centered over 0. Let's assume the null hypothesis is true. So what we're going to assume is that this is true. Now, we don't know it's true. We're trying to, as researchers, make a determination on which is more credible, the null hypothesis or the alternative hypothesis. If the null hypothesis is true, then as I take samples and I estimate it, my true statistics are going to pinging around 0, right? I'm never going to get exactly 0 because I don't have the full population. I have a random sample from the population. So I can get estimates that are really far in these tails. Even if the true value is 0, I can still get, like, say, -2. I can get a positive 2.2, right? If I just get a random sample and I just get bad luck, and I can end up in the tails. So what the type 1 error rate is it basically says, okay, my research findings are probabilistic. I want to basically have a type 1 error rate, most commonly of 5%. So that means I'm going to accept that when I get my sample, I'm never going to get exactly 0. I know I'm going to have to get close to 0, but the question I have to ask as I do a hypothesis test is, how close do I have to be to 0 before I can safely say, yeah, 0 is consistent? That is, this null hypothesis is consistent with the data. On the other hand, how far do I have to be away from 0 before I say, no, the 0 hypothesis is not consistent with the data? So this is why we talk about the type 1 error rate. So because research findings are probabilistic, we're assuming the null is true here, I can just get really extreme values like in these tails, right? So what we as scientists usually do is we adopt the rule that alpha equals 0.05. That is, we call this right here, this is the type 1 error rate. And usually we set it at 0.05. And what that means, if we're doing a two-tailed test, well, let me step back for a second. What that means is that the area in these tails is 0.025 and 0.025. Why? Because what I want is I want overall 5% chance of rejecting the null hypothesis. And so what that means is if the null hypothesis is true, then I know I should be retaining the hypothesis, right? This should be what we want to do. But sometimes I can get data that just because of bad sample that's so far away that the data is not consistent with this hypothesis. And what we do is we say, well, let's accept that we're going to make a mistake 5% of the time. So that means 5% of the time I'm going to be in the tails of this distribution. I'm going to get a value that's so far away from zero, even when zero is true, because my sample just had bad luck. Well, 5% of the time I'm in these tails. And what that means if I'm doing a two-tailed test, that 2.5% of the area needs to be in the left tail and 2.5% of the area needs to be in the right tail. So this is why when you see alpha over 2, what we're really signifying is a two-tailed test. Two-tailed test. So that's alpha. It's called the confidence level or the significance level, the type 1 error rate. All means the same thing. And I can do different things, right? I can come in and say, well, I want actually a confidence level of 10%. So then if my confidence level, if my alpha is 0.01, sorry, that's 1%. Well, then I'm saying, okay, I'm going to accept that I'm not going to get exactly zero, right? But I'm going to accept that I'm going to reject the correct null hypothesis 10% of the time. That's putting 5% area in the tails. So you can choose different alpha levels of significance. Most commonly, 0.05 is going to be chosen. But two other common numbers you'll see are 0.10 and 0.01. So those are the three most common levels of alpha. And when we construct a confidence interval, notice we write 1 minus alpha percent confidence interval. So if alpha is 0.5, then a 1 minus alpha percent confidence interval, or a 1 minus 0.05, or a 95% confidence interval. So these two are the same. An alpha of 0.05 implies a confidence level of 95%. And that's what this statement right here means. So what you have to do, you never have to calculate alpha. These problems will always give you alpha. So, we'll look at some problems down below. But, it says give you a 95% confidence interval there. So that alpha there is going to be 0.05. 99% confidence interval, the alpha there is 0.005. So the alpha is always given. And based on what you're doing, so, you can do a one-tailed test or a two-tailed test. So if I do a two-tailed test, we've already talked about that. If alpha is 0.05, that leaves me 0.025 area in both tails. So this is alpha over 2. So that's why that's a two-tailed test. But if I do a one-tailed test, same distribution, I can say I can test the null hypothesis. Oops. The null hypothesis that mu is greater than 0. And then, because it's a one-tailed test, I can put all of the error and one tail over here. And the reason I might do that is because, look, if I do a two-tailed test, I only get 2.5%. This Z crit is going to be, I'm more likely to reject the null. Remember, normally we want to reject the null. We're going to be talking about hypothesis testing in the next few weeks. But if you have this Z star versus this Z star, right? This one is a lot smaller. So you're more likely to reject a null hypothesis when you use a one-tailed test. So that's why people will use a one-tailed test. What we say is a one-tailed test has more statistical power. Statistical power is defined as the probability of correctly rejecting the null hypothesis. You don't have to be too comfortable with statistical power in this class, but going to more immediate level classes, this will be a concept that comes back. In this course, what we're worried about is alpha. That's type 1 error rate. There's something else called type 2 error rate, which we're going to talk about a little bit. And this is what statistical power is. And again, this is a little beyond the scope of the class. Beta, type 2 error, we're going to be talking about a little bit, but really our key focus is here. Alpha, type 1 error rate. We're going to be dealing with this pretty much every week going forward. It's a number that we take as given because as a researcher, you just specify what confidence level you want. Most commonly, you want a 95% confidence level. So this Z alpha over 2, going back to that, we've talked about the alpha, and so actually I'm gonna introduce this down here with an example. So I'm gonna do example 1 right now, and so let's see what this problem is. We want to know the mean of a variable x for a population. So we have a sample size of 60. We find our x bar, and we find our sample standard deviation. So this means if I look at the distribution of x, not x bar yet, it's normal. It's got a 35.2 mean. Actually, hold on. Actually, I don't know. Our estimate of mu is 35.2, but I actually don't know the center of this distribution yet. And actually, I also don't know the variance. Well, let me back up. What we're going to assume is that, well, I don't want to keep all that. So I don't know mu and I don't know sigma squared, right? Because they're not given to me in the problem. Do I actually know enough to say that this is a normal distribution? Think about that for a second. The answer is no. There's nothing in these 2 or 3 sentences that say anything about a normal distribution. So actually, I need to back up. We're not saying X is normally distributed. We're not telling us anything other than these estimates and the sample size. So I need to back up. I can't say that because it says nothing about X being normally distributed. What I can say is X bar is normally distributed. I can say that because there's a large sample size. When n is larger than 30, we're going to be in case 1 above, where we assume that sigma is known. So when we say sigma is known, we're going to basically be using that as our estimate of sigma. So again, X bar, it's going to be normal. It has some mean, which we don't know. And the variance is going to be the sample standard deviation, 12.5 squared, divided by the square root of n, divided by the square root of 60. And so this value that I put here, what I just put there, is that value. Now we can, of course, we know that the square root of that is the standard deviation or the standard error of X bar. And using the formula above, we can calculate it, right? It's the sample standard deviation, which is going to be little s, our estimate there, over the square root of 60. So we're just plugging in this information. And when we do, we find the standard error is 1.6. Okay. So that's the first part. So if you're solving for the confidence interval of the mean, there are three things you need. I think we'll list these out. Number one is alpha. So alpha, it always gives you in the problem. If we have a 95% confidence interval, what is alpha? It is 0.05. The second thing we need the estimate for the, let me write it this way. We're going to estimate that with our sample standard error. And that is, we've already computed that as 1.6. Then we need to find Z alpha over 2. So X bar is going to be usually given. So our confidence interval is of this form, right? It's written right here. I'll write it out over here too. X bar. We already know X bar, right? That's going to be 35.2 plus or minus. Now we have Z alpha over 2, which we need to still compute. And then we've already found the sample standard error, which again, remember, that's our estimate of the population standard error. And that value is 1.6. So the last thing we need to form this confidence interval is Z alpha over 2. So how do we get Z alpha over 2? Well, we're going to need to use our trusty Z tables. So alpha over 2 is 0.05 over 2. And I like to add, these are Z crits, I like to add so I need to find the critical value of Z. And we're going to draw our Z distribution. So over 0. That leaves 0.025 area in the tails. And it's a two-tailed test. Remember, this distribution is symmetrical. So negative Z will equal positive Z. So there's two ways to get this number. Okay, so now what I'm going to do is I'm going to open up my trusty Z table that we're going to be using this semester. And I'm looking for the probability of 0.25, right? So what I need to do, let me clear all this for a second. I can find it in the left tail. So let me do that. 0.0. Right here. Negative 1.96. Negative 1.96. I can also find it in the positive tail. And I'm looking for 0.025 to the right. So that means I need 0.0975. Which I know is actually going to be 1.96 because it's a symmetrical distribution. So if I pull all this back, oops. So if I pull all this back, what I just found was that these Z's are negative 1.96 leaves 2.5% of the area of the distribution there, and 1.96 leaves 2.5% of the area there. So it's a two-tailed test, and the problem actually doesn't state that. So if the problem doesn't state it, we just assume it's a two-tailed test. A two-tailed test is much more common. So I plugged that 1.96 I got out of my Z table. And you can see here the 3 steps to getting these confidence intervals are: determine alpha, determine the standard error of the mean, and then find Z crit. Z crit's going to be tied to what the alpha is and whether you're doing a two-tailed test. And then step 4 is you plug and solve. And so here is where we solve for the confidence interval. So 32, 38 is that interval. So what that means, if I interpret this, that I'm 95% confident that the true value of the mean is in this interval 32 to 38. Look, you can be really technical on interpreting the confidence interval. I don't want to really drill down to that level. I want you to think of the confidence interval as an interval estimate that also conveys the uncertainty. So if I would say here the mean is 35. You know, that's a decently wide range. I'm not too confident that I'm very close to the mean, right? If the confidence interval had been like 34 to like 36, I would be really confident. I would say there's a decent amount of error here, and it's probably because we have a smaller sample size of 60. Okay, so I'm gonna let you all do the second example on your own. You're gonna go through those first 3 steps. Then the 4th step is plug everything in, right? There's many more examples in the book. So I'm not going to drill down too much on you guys about interpreting the confidence interval. I will just say this. I think this picture is really great. What you need to remember is that the confidence intervals are random. What's not random are the population values, mu. Mu is 65. I'm trying to estimate the 65 with a sample of data. Now I take a random sample of data. And it could be, I just, in this case, just got everyone that was on the positive high end. I took 36 people, and when I take 36 people, that can happen. So what happens is that if I were to conduct this 20 times or 1,000,000 times, an infinite number of times, 95% of these intervals, if I'm creating a 95% confidence interval, would have the true parameter mu. So the parameter mu is fixed. The thing that's random and fluctuating, because you have a random sample, is the estimate of the confidence interval. So notice how 19 out of 20 or 95% have the true parameter mu. So the very last thing I want to touch on is this idea of a margin of error. Give me 1 second to pull open textbook. Okay. So this week you have two chapters to read. They're pretty small. So the margin of error is something we're not going to talk too much about, but it's probably something you've heard of. So remember, we create our confidence interval of the form x bar plus and minus standard error of x bar times z crit alpha over 2. So this part right here is called the margin of error. And really what the margin of error expresses is how precise our estimate is. And you can kind of see it, right? If the x bar is 50 and I have a confidence interval that's 0 to 100, I have another one that's 49 to 51. Clearly, this one is a more accurate estimate, probably because I've taken like 1,000,000 people to estimate that. Here, maybe I've taken like 2 people, so it's a bigger confidence interval. So the margin of error tells us how wide the interval is going to be. Notice you're plus and minusing the margin of error. And again, it tells us how much error there is in our estimate. So the error, there's 2 things that affect the margin of error, right? There's the actual error or imprecision in our estimate, but there's also how confident we want to be that our confidence interval has it. So if we're a 95% confidence interval, 95 out of 100 of these intervals are going to have the true mean right in there. If I compare that to 75% confidence interval, what actually happens is the interval size shrinks. And that's because now I'm only 75% sure that the interval I have has a true mean. And because it's smaller at 75%, it's more likely to not have the true mean, right? So I would just say the margin of error, there's two things in it. I would think of these things independently. This is just a decision Z alpha over 2 that the researcher makes. 95% confidence level or a 5% error level for alpha are the standard places that we start. And then this is the actual error in the estimate. So as you have more error in the estimate, the margin of error goes up. As you want to get less confident that your interval has it, that is, you go from 95 to 75, the interval is going to get smaller. So we're not going to be dealing with the margin of error too much. You might see it here and there, but you don't need to worry about studying it or anything like that in great detail. But you should read about it and be familiar with its basic nuts and bolts. Okay. Thank you for listening in. That is all for today.